Your eye color is not decoration. It is inherited survival technology. What looks like a simple shade is actually the result of thousands of years of environmental pressure, migration, and genetic filtering. More than 70% of humanity carries brown eyes. The rest carry variations born from mutation, changes that rewrote human biology in subtle but powerful ways. Brown eyes are the original blueprint. Their depth comes from high concentrations of melanin, a pigment capable of absorbing up to 90% of incoming light. That absorption is not aesthetic, it is protective. Under intense equatorial sunlight, early humans faced constant ultraviolet exposure. Without sufficient melanin, cellular damage inside the eye would accumulate rapidly. Brown pigmentation acted as a built-in filter, intercepting radiation before it could disrupt sensitive tissue. But protection wasn't the only advantage. High melanin reduces internal light scatter, minimizing glare and improving visual precision in bright conditions. When sunlight is harsh, brown eyes remain stable. This is why they dominate populations near the equator. It wasn't preference, it was performance. And yet, under low light, brown eyes can reveal subtle flashes of amber or gold. That shift is not a change in color, it is physics. Light interacting with layered iris structures beneath the surface. Then, something changed. Thousands of years ago, a mutation altered melanin regulation in the iris. Before this event, every human had brown eyes. After it, a new variation appeared, blue. Blue eyes do not contain blue pigment. There is no blue dye in the iris. Instead, melanin levels are dramatically reduced. When light enters, shorter wavelengths scatter back outward while longer wavelengths pass through. The result is structural coloration, the same optical principle that makes the sky appear blue. This mutation spread rapidly through northern Europe. Why? Some researchers argue that lower melanin allowed more light to reach the retina, potentially improving vision in dim winter environments. Others suggest rarity itself became advantageous. When a trait is uncommon, it draws attention. Attention influences mate selection. Selection drives expansion. Gray eyes push this reduction further. With even less melanin, light disperses across multiple wavelengths, creating a cool steel tone that shifts subtly between silver and slate. But lower pigmentation comes at a cost. Increased UV sensitivity is the trade-off. Every color variation reflects the same equation. Adaptation always demands balance. Genetic evidence from ancient human remains revealed something that forced scientists to rethink eye color evolution entirely. Early Europeans with blue eyes often had dark skin. That discovery overturned a long-standing assumption that light eyes evolved alongside pale skin. They didn't. The mutation that reduced iris melanin operated independently. Eye color followed its own evolutionary path, shaped by pressures we are still trying to fully decode. When humans migrated into regions with weaker sunlight, pigment levels began to shift. Lower melanin allowed more photons to reach the retina. In long northern winters, where daylight was scarce and dim, that increase in light transmission may have offered a subtle visual advantage. But evolution never gives without taking something back. Reduced melanin means reduced protection. Lighter eyes are generally more sensitive to glare and ultraviolet exposure. Over time, that sensitivity can increase vulnerability to certain light-related conditions. Adaptation is always a trade-off. Gain sensitivity, lose shielding. Now contrast that with extremely dark eyes. What appears black is not a separate pigment. It is an extreme concentration of brown melanin, so dense that almost all incoming light is absorbed. Absorption reduces internal reflection. Reflection causes glare. Less glare means more stability in intense sunlight. In equatorial environments where UV radiation is relentless, this saturation becomes an advantage that compounds over decades. Darker irises filter harsh light more efficiently and maintain consistent visual clarity under extreme brightness.
It is maximum defense. Amber eyes follow a different biological pathway. Their golden tone comes from elevated lipochrome levels combined with relatively low melanin interference. Unlike blue or gray eyes, amber does not rely heavily on structural scattering. The color remains stable under changing light conditions. It does not shift dramatically between shadow and sun. That consistency creates visual intensity. Similar pigmentation patterns appear in certain predatory animals. Humans may subconsciously associate that hue with alertness or dominance, not because of superstition, but because our brains are wired to recognize contrast and signal strength. Then there is heterochromia. When melanin distribution diverges between the two irises or within one iris, symmetry breaks. The human brain instinctively searches for symmetry in faces. When it encounters asymmetry, attention increases. That is why heterochromia feels striking. Across all these variations, one principle remains constant. Eye color is not decoration, it is environmental data encoded in pigment. And every surviving variation passed the same test. It did not eliminate advantage.
Eye color does more than regulate light. It quietly influences perception, not just how you see, but how others interpret you. Melanin concentration changes contrast inside the eye. In darker irises, the transition between pupil and surrounding pigment is subtler. In lighter irises, pupil dilation becomes more visually pronounced. That difference matters. Humans unconsciously monitor pupil size. Expansion can signal interest, arousal, stress, or cognitive effort. In lighter eyes, those micro-adjustments are easier to detect. In darker eyes, they are more concealed beneath dense pigmentation. This creates a subtle perceptual effect. Lighter eyes are often described as expressive, transparent, or emotionally readable. Darker eyes are frequently labeled intense, controlled, or mysterious. These interpretations feel psychological. In reality, they are optical consequences of pigment density. Even light sensitivity varies. Individuals with lower melanin levels in the iris tend to report greater discomfort under bright conditions. Some studies suggest slight differences in glare tolerance and visual adaptation speed between lighter and darker eyes. None of these variations determine intelligence, personality, or character, but they reflect how pigment influences sensory input. Culture amplified these physical differences. In parts of medieval Europe, rare eye colors were romanticized or feared. Green and blue eyes became associated with mystique or supernatural perception simply because they were uncommon. In equatorial regions, darker eyes were linked with endurance and resilience under harsh sunlight. Over time, societies layered symbolism onto biological adaptation. But symbolism does not change biology. No eye color is superior. Each represents optimization under specific environmental constraints. Brown eyes maximize UV filtration. Blue and gray may enhance sensitivity in low-light climates. Hazel provides flexible balance across variable conditions. Amber maintains high visual stability with striking uniformity. Extremely dark pigmentation offers maximum protection where radiation exposure is constant. Modern migration has blurred these geographic patterns. Today, eye color appears across continents independent of original climate pressures, yet the underlying genetic mechanisms remain intact, preserved within the iris. When you make eye contact with someone, you are observing the result of climate, mutation, mate selection, and survival filtering layered across thousands of years. The pigment inside your eye is not random. It is biological memory expressed through light. And the fact that such small variations can alter perception, adaptation, and cultural meaning reveals something deeper about human evolution. Your eyes do not merely capture the world, they reveal it.
For most of human existence, survival depended on marginal advantages, not dramatic mutations, not instant transformations, subtle adjustments that improved resilience by a few percentage points, tolerance to radiation, sensitivity to low light, stability under glare. Eye pigmentation became one of those adjustments. No surviving eye color is accidental. Every variation present today endured thousands of years of environmental pressure. If a mutation severely reduced survival odds, it vanished. If it preserved function or offered even a slight advantage, it persisted and spread. Brown eyes supported early populations under intense solar radiation. High melanin absorbed ultraviolet exposure before it could damage delicate ocular tissue. Over generations, that protection compounded. As humans expanded northward into regions with weaker sunlight, pigment reduction emerged. Blue and gray eyes allowed greater light transmission, potentially improving visual performance during long winters with limited daylight. But increased sensitivity came with cost. Reduced shielding meant greater vulnerability to brightness and UV exposure. Hazel and green eyes represent balanced states. Moderate melanin levels provided partial protection while preserving adaptability in temperate climates with mixed lighting conditions. Amber pigmentation followed its own trajectory, producing stable, uniform coloration that stands out visually without relying heavily on structural light scattering. Extremely dark eyes maximize absorption efficiency. What appears black is simply dense brown pigmentation filtering nearly all incoming light. In equatorial regions where radiation is constant, this offered durable, long-term protection. Even heterochromia, the disruption of pigment symmetry, demonstrates that development tolerates variation when function remains intact. Evolution filters for viability, not aesthetic uniformity. Modern technology has reduced many of the environmental pressures that shaped these traits. Artificial lighting, indoor living, sunglasses, and global migration have diluted geographic correlations. Yet the genetic architecture remains embedded in the iris. When you stand in front of a mirror, you are not observing a cosmetic feature. You are observing accumulated adaptation. Inside that narrow ring of tissue lies evidence of migration across continents, exposure to shifting climates, and generations who survived long enough to pass that pigment forward. Your eye color is a compressed biological timeline. It is proof that someone before you adapted successfully to their environment. Thousands of environmental decisions made by nature converge in a single visible trait. So when light enters your eyes, remember what you are truly seeing. Not style, not coincidence, but evolutionary engineering refined across millennia and carried forward precisely into you.